Good afternoon, folks. How's everybody doing?
Good afternoon,
Hey,
Professor.
I'm
Very
Professor.
good.
Thank you.
Hello. So as you know, we had a midterm, and I'm sure you already seen your scores and the solutions. The average was 68%, which actually is quite decent for 1C midterm 1. I have seen a decline in the average scores in recent years. It's not just for physics 1C, it's across the board. And it's not just in my class, actually. I've been talking to my colleagues, they all feel the same way. Some time ago, the typical average for the 1C test in my class were in the mid 60s. And it's been going downwards in the past few years. But this one is actually, by comparison, actually pretty good, 60%. So I've told you before that I had very good feelings about this class because, the way you ask me questions and the type of questions you ask me that suggests that it's a very active class who are really interested in learning this stuff. So I think that's reflected in your test scores. So I'm happy so far, even though individually, I'm sure a lot of people would wish that they could have done better. This is only one test, and because of the way we structure the scores, having somewhat unsatisfactory performance in one test is not going to be detrimental to your overall score. You just have to work harder and make it happen next time, and you can still end up with a good score, good grade at the end. Okay, so keep up the good work if you did well. Otherwise, I'm sure there's plenty of opportunity for you to catch up. Do you have any questions before we move on to today's agenda? Okay, if you don't have anything at this point, you can always talk to me individually. Okay, so what we have today is a discussion of chapter 29, or in the older editions, in the 10th edition of chapter 28. This is the first chapter of the magnetic field. So let me share a screen with you. Okay. You can see the summary, right?
Yes, Professor.
Yep. Okay, good. So again, for the first time, we're seeing the other side of the coin, the magnetic phenomena. It follows a pretty good logic, pretty tight logic. We started out with, charges, stationary charges, electrostatics, and that covered chapter 23, 24, 25, and 26. And then starting from chapter 27, we finally allowed charges to move to form a current, and then you talk about circuits, that sort of thing. But historically, people have been studying, electrons, the electrical circuit, that sort of thing, without realizing that they are actually creating a magnetic field as a byproduct. They didn't realize that until by accident somebody discovered that. Remember there was if you study this chapter, there was this guy by the name of Oersted, right? He was preparing for a lecture demonstration of electrical circuits, and when you flip the switch to turn on the current, what happened? Just by chance, he had a compass nearby, and that compass, what happened to the compass? The compass turned. Okay, now the compass was to respond to the Earth's magnetic field. We know for a long time the Earth had a magnetic field, and the compass really is just a bar magnet, so it aligned with the Earth's magnetic field lines. People knew about magnetic phenomena for a long time. They also knew about electrical phenomena for a long time. But this marked the first time, even though it's just by accident, that people realized that electrical current can cause a magnetic field. And that's how it caused the compass to turn. Okay, so now that we allow charges in motion, so we have a moving charge or a current, then we realize that it does not only respond to an electric field, it also responds to a magnetic field because it has created its own magnetic field. Okay, so moving charges create not only an electric field, but also a magnetic field. And current is just a whole bunch of moving charges. Okay, so they can also produce a magnetic field. So how does a moving charge produce a magnetic field? That, in fact, is the subject of the next chapter, so-called sources of the magnetic field. Okay, and in this chapter, we don't get into any details on how the moving charge creates a magnetic field. We just have to know that a moving charge creates a magnetic field, and therefore it also responds to an existing magnetic field. Okay, and that's all I have to know. As far as the details how the field is created, that's chapter 30, the next chapter. What we focus on this chapter is that once we have a magnetic field, which somebody else created, okay, you throw a moving charge in there or throw a segment of current in there, what's going to happen? You know there's going to be a force acting on it, okay? Because the moving charge or the current produces its own field which interacts with the existing field. The two magnetic fields interact, and the result is a force. Specifically, what do we call that? We call it the Lorentz force. And it's all about applications of Lorentz force. So the centerpiece of this chapter, the number one concept in this chapter, is the Lorentz force. Okay, so we look at how how a magnetic field can produce a force on moving charge, and what are the applications of that. And then in the next chapter, we'll take a step back and look at how a moving charge can create a magnetic field. Okay, so that's the connection between electricity and magnetism. For the first time, we're seeing the connection, but the connection doesn't end here. There are other ways to connect electricity and magnetism, and you will see starting from chapter 31, because after all, we are only getting into the second of the four Maxwell's equations, and there are two more. So you will see when all is written down, you will find that there's just so many ways to connect electricity and magnetism. Okay, we're just seeing that for the first time. All right, so we're going to focus on what a magnetic field can do to a moving charge. And what that means is that we look at the Lorentz force. Okay, the Lorentz force is the magnetic force exerted on the moving charge, or a segment of current, because that's just a whole bunch of moving charges. Okay, now the magnetic force, the Lorentz force, takes the form of QV cross B. So there's a cross product here. There's a cross product. We've never seen a force expressed as a cross product, even though we have seen cross products before, in angular momentum. And the textbook doesn't really specifically talk about why this force happens to be expressed in terms of cross product. I just said that's experimental fact. Okay, now in my video lecture, I went into this a little bit. I want to show you it's not just a coincidence. Okay, the cross product is very natural here, because if you take A cross B, vector A cross vector B, you get a resultant vector C, which is perpendicular to both vector A and vector B, right? That's by definition the cross product. In our case, we have a magnetic force, the Lorentz force. It depends on two other vectors, the velocity of the particle in motion and the magnetic field that it is exposed to. Turns out that the resultant Lorentz force is perpendicular to both V and B, B being the magnetic field. This is not just an experimental fact. There is profound reason behind it, and that reason is symmetry. Okay, it's profound, but it's simple to understand. Okay, and I made that argument in my video lecture, why it has to be why the Lorentz force has to be perpendicular to both B and V, using symmetry argument. So please review that. It's something simple yet powerful. Okay, so we have a vector which is perpendicular to two other vectors. So the only way we know how to do that is by virtue of cross products. So it's very natural. It goes like Q B cross B. Okay, so that's the Lorentz force. And given this Lorentz force being equal to V cross B, we know it's perpendicular to B, and perhaps more importantly, it is perpendicular to V, the velocity. When a force is perpendicular to velocity, that is a very special case. Usually, you don't have something like that. Where have you seen before in your physics 1 series studies that when the force is perpendicular to the direction of motion? You've seen that way back in 1A, physics 1A, chapter 4, the first time.
It's from centripetal acceleration, so circular motion.
It has to do with circular motion, that's right. Okay, in order to move us in a circle, there has to be force pulling into the center of the circle. That's called centripetal force. It is perpendicular to the direction of motion. The centripetal force is responsible for turning you around so you can move in a circle. Does the centripetal force make you go faster or slower? No. At the tangential force will make it go faster or slower. In order to make it go faster, the force has to push you from behind. In order to make it go slower, the force has to pull you from behind. Okay, the force has to be either parallel to the direction of motion, in which case it makes it go faster, or anti-parallel, in which case it makes it go slower. But here, this force is perpendicular to the direction of motion. It is neither pushing the particle nor pulling on it. Therefore, this force, the Lorentz force, cannot make the particle go any faster or slower. The only thing it can do is to turn it around, to change direction of motion. Okay, so from the language, using the language of work and energy, we say the Lorentz force does zero work on the moving particle because F dot V, that's the power delivered. And F dot V is how much in this case? It's zero because F and V are perpendicular to each other. Okay, so the Lorentz force doesn't do any work. The only thing it can do is turn the thing around. Okay, electric force can do work. Electric force can make the particle go faster or slower, can impart energy to the particle. The Lorentz force doesn't do that. It cannot take energy from the particle, nor can it give energy to the particle. It can only turn around. Okay, that is a very important characteristics of the Lorentz force. Okay, and it's different from the Coulomb force. Only the electric force can accelerate a particle in terms of giving it, a greater speed. Okay, and then there are two types of Lorentz forces. The Lorentz force on a single moving charge, and from that we can derive the Lorentz force on a segment of current. Okay, we have this derivation in the video lecture. Basically, what you have is you consider a segment of current, a segment of a wire. Why a segment? Because in a given segment, you have a given number of moving charges. Each charge is subject to a Lorentz force, which is QB cross B. Okay, you cannot think of an infinitely long wire because it's got infinitely large number of moving particles. Each particle receives a force, and you get total force of infinity. That doesn't make any sense. Okay, so you have to isolate a little segment and look at how many moving charges are there responsible for the current, and how much does each one, what is the force on each one of them? Then you add all these forces up. Then you will get the Lorentz force on the segment of current. It is IL cross B. Clearly, it's proportional to current because when you double the current, okay, for the same number of moving charges, you're essentially making each particle on average move twice as fast. And therefore, each particle will receive twice as much Lorentz force. Okay, so it makes sense. That's proportional to I. So these are the two cases, but the fundamental case is the charge is the force on a single moving charge. From that, you can derive the force on a current because it's just a bunch of moving charges. Okay, now examples of Lorentz force. Once again, you can look at specifically on a segment of current, right, which is IL cross B. But another important case is on a current loop because current often form loops. Okay, and a current loop, when you have a current loop, if you have only a single loop, then of course the current running through the entire loop is the same. Okay, it cannot be I1 here, I2 there. It doesn't make any sense because it violates the conservation of charge. It has to be the same current. Now, the loop can have totally different arbitrary shape. It doesn't even have to be two-dimensional. But when you put this current loop in a uniform magnetic field, you can show very easily that the total force acting on this loop is zero. Okay, you just, IL cross B, that's the force on the segment of L, but here you have to break it down to DL, right? Because they're different, potentially you can have different field at different locations. So you go DF equals I DL cross B. I is the same everywhere. B is the same everywhere because it's a uniform field. So when you integrate, the only thing left inside the integral is DL. And that, when you integrate over the entire loop, what is DL equal to? That's zero. DL is a vector. You just add, a whole bunch of vectors, you go back to yourself, it's zero. So no matter what the shape of the loop is, if you put it in a uniform magnetic field, there is no net force on it. Okay. However, it doesn't mean the magnetic field does nothing to the loop. It actually can turn around, can flip it because there's a torque. Okay, there is a torque. So you have zero net force, but non-zero net torque. This is analogous to the case of electric dipole. An electric dipole, you put it in a uniform electric field, it's gonna get two opposite forces in the opposite direction, the same magnitude. So the net force is zero. But it's like this is what's called a force couple. Okay, you get force misaligned of the same magnitude, opposite direction, but they're misaligned. So that's going to tend to turn the thing. It produces a torque acting on this electric dipole. So you think of the electric dipole and the current loop to be analogous to each other. One for the electric case, the other for the magnetic case. Okay, it is very important to realize that a current loop in a magnetic field is subject to a torque to make it turn, because that is the mechanism behind important applications such as the electric motor. An electric motor, what does a motor do? You have it in an electric car, for example, right? It replaces the engine, right? It pushes the car forward. What does the motor do exactly? You plug into the power supply, what happens? It turns, right? You are turning electrical energy into what? Mechanical energy. That's what a motor does. So how does the motor turn when you plug into to a power supply? The idea is very simple. You have in the motor, you have a fixed magnetic field created by permanent magnets. Okay, you don't have to do anything, it's just already there. But in this magnetic field, what do you have? What do you put in? You put in a current loop. Okay, in fact, it can be multiple terms. And then you just plug in a power supply so that this loop now carries current. And automatically, what happens? This loop will now be subject to a torque produced by the magnetic field. Then it starts to turn. That's how a motor works. Okay, so in the electric car, the design is much simpler than a conventional gas-powered car, because there's no engine, there's no transmission, nothing like that. All you need is an electric motor. An electric motor, but the only tricky part is how do you supply electricity to the motor, and that is not supplied by AC power source, of course, because it's a moving car. It's supplied by the battery pack. Okay, so it's just a matter of battery pack plus an electric motor. That's why the design is much easier. Because of that, the maintenance cost is much lower by comparison, because there are few parts. The only part that's quite expensive, at least for now, is the battery pack. Okay, the motor itself, even the Tesla motor, it's a fancy car. It's not cheap. The car is not cheap, but the motor, the motor is not expensive. Last time I checked, the motor itself costs under $1,000, brand new. Because it's not hard to make. I mean, the gas engine, that's a totally different story. It's much more complicated. Like everything is sealed and under pressure. That's a lot more expensive to produce. So the motor is nothing. It's just a battery pack that's more expensive. Anyhow, so that's a very important application. Okay, and also, what happens when you put a Lorentz force on a moving charge, a single moving charge? You have a moving charge and it's inside inside a magnetic field. Okay, then there's a Lorentz force. Now remember, the Lorentz force is always perpendicular to the direction of motion. It doesn't speed up, doesn't slow down, but as a result, it's going to turn around, right? It's going to turn around. So what kind of motion do we have? Well, in the most general sense, it's helical motion. Helical motion. Helical motion is really circular motion going forward, with the loop going forward. The reason why it can have a loop going forward is because when V is parallel to the B field, the velocity is parallel to the B field. What's V cross B equal to? 0, right? V cross B equal to 0. So therefore, if you have a B field pointing this way and you shoot a particle in the same direction, this particle receives no force. Okay, because V cross B equals 0. There is no Lorentz force. And if a particle moves perpendicularly to the B field, then it's going to be moving in a circle because V cross V is not zero. However, in a most general sense, a particle, here's the magnetic field pointing this way. You have a particle coming in an arbitrary direction. This initial velocity of the particle has two components, one along the direction of the B field, the other perpendicular to the B field. The components along the B field never changes because that component, remember, V cross B equals zero. They're parallel. Okay, so it sort of does circular motion in one plane, but keeps on going forward in the direction along the B field, because that direction, the velocity doesn't change. Okay, so that's called a helical motion. So that's something to know, and it's not hard to analyze that motion. Okay, so those are some typical examples. And in the real world, what do we use the Lorentz force for? Well, here are just some examples. There are many more examples. Q over M device. Okay, in fact, one of the labs that you'll be doing is based on that. In that lab, we actually study what's called E over M. Q is the electron charge, E. Okay, and so you have a beam of particle, and they're charged, and they're in motion. You put it in a magnetic field, it bends into a circular path. By studying the radius of that circular path, you can in fact find the so-called charge to mass ratio, Q over M. And that is important because Q over M is unique for any different type of elementary particles, electrons, protons, any charged elementary particle. They all have a different Q over M ratio or charge to mass ratio. So you can identify what kind of particle is it. Is that a beam of electrons, or a beam of protons, or is it something else? You can tell. Okay, so Q over M device using Lorentz force. And a variation of that is the mass spectrometer used probably in your chemistry class, chemistry labs, mass spectrometer. So you have a bunch of ions. They have the same charge, but they don't have the same mass. Okay, they're different isotopes, right? Different isotopes. When we shoot them through a magnetic field, they're going to be bent around to turn into a part of a circle. And by figuring out where they land, you can find the radius of that circle, and from that you can identify the mass. Okay, you can identify the mass. So that's called a mass spectrometer. It's actually a toy invented by physicists. So these are Q over M devices, and you have so-called particle accelerators. That's one of the greatest areas of application of the Lorentz force. I mean, in the video you saw the so-called cyclotron, right? The cyclotron is the first example in which the Lorentz force has been used in combination with electric force to accelerate the particle moving in a circle. Okay, the original cyclotron was very small. It was designed by Lorentz. It was fit into the size of his palm. So the idea was you use an electric field to accelerate the particle, because only the electric field can impart energy, can make it go faster. Okay, but if you only use the electric field, then the problem is that the particle, such an electron, can easily be accelerated to a very high speed, and then before you know it, they're going to go out of the little chamber that you create for it, unless you build a chamber 3,000 miles long, which is impractical. So what you want to do is you don't want the thing to shoot in a straight line because that's going to take too much space. So rather, you want the thing to turn around while being accelerated, keep on being accelerated. So how do you make it turn around? Use the magnetic force, the Lorentz force. So the Lorentz force pulls the particle into a circle while the electric force make it go faster and faster. Okay, that's the central idea in a design, a very elegant design called the cyclotron. And then later on, based on the same design, physicists has made the device bigger and bigger and bigger. Today we have, these particle accelerators the size of a small city. Okay, and each has a big name like the Bevatron, superconducting super collider, whatever, Brookhaven National Lab. All these we're talking about gigantic devices costing billions to build and billions to maintain. But they're all based on the same idea. The electric force accelerates the particle, the magnetic force turns the thing around into a circle. Okay, That's particle accelerators. And in nature, we have the Earth's magnetic field. The Earth is not the only planet that we know that has a magnetic field. Other planets also do. And the exact origin of the Earth's magnetic field, we know in principle where that come from. Okay, we got molten lava, so we get actually charged particles moving in the Earth's core. But that's a very complicated process. Even with today's technology, with today's science, we do not know exactly how to model the Earth's magnetic field and to predict exactly how it's going to change. We do know there is geological evidence that the Earth's magnetic field has been changed back and forth many times. Today, the North Pole, the magnetic North Pole, is close to the geographical South Pole, and vice versa. Okay, you know that, right? I mean, the geographical North Pole, that's where Santa lives, right? That is not the Earth's magnetic North Pole. It's the magnetic South Pole. Why? Because when we use a compass, the compass points north. So that is called the North Pole of the compass because it points north, right? It's actually north-seeking pole. Why does it seek that direction? Because that direction is the Earth's magnetic South Pole. That's what's been attracted to the magnetic South Pole. Okay, so the magnetic South Pole and the Earth's North Pole, they are at the same location, or more precisely, they're close to each other, not exactly the same location. That location keeps on shifting. The magnetic North Pole and South Pole keeps on shifting. Currently, as you probably already know, the magnetic North Pole, the magnetic South Pole of the Earth is in the Hudson Bay area of Canada, close to the geographical North Pole, but not exactly the same. They're about 1,000 kilometers apart from each other. But there is the Earth's magnetic field. It's not just for navigation, for compass. It's not just for certain pigeons to figure out how they get home. These are incredible, by the way. The pigeons are incredible. They can find their nest from thousands of miles away using the Earth's magnetic field lines as a guide. It's incredible. But there is even more important, more crucial applications of the Earth's terrestrial magnetic field as far as how humans and other species can survive on the surface, because it captures the high-speed charged particles coming from the sun and from the cosmos. Okay, these high-speed charged particles, when they hit the surface of the Earth, they can go through our body. It's not good for us. They can cause cancer. Fortunately, most of these particles do never make it to the surface of the Earth. They are being trapped by the Earth's magnetic field. Because of the Lorentz force, they are forced into helical motion and they go back and forth around in between the two poles, like they've been kicked back and forth between the two poles. And you can see in the the way the Earth's magnetic field is the field lines is curved. It really traps these particles, and the particles, instead of falling down to the surface of the Earth, they end up doing helical motion back and forth, and they spend more time near the two poles. So there's a higher concentration of these particles near the two poles, and these are high-speed particles. They move at a very high, they have a lot of kinetic energy, so when they strike the air molecules, they can give energy to the air molecules. They cause the air molecules to emit light, and that's the northern light, or aurora borealis. Okay, so we turn these harmful particles into a light show. That is what the Earth's magnetic field can do to protect us. Okay, interestingly enough, the Earth's magnetic field can shift, and it has shifted many times. And there are historically, geologically, there were times where the Earth had almost zero magnetic field because it's switching between the two polarities, and species did survive. So it's not something that we can totally live without for any moment. But it's interesting to see how species have adapted to that, or with for durations with Earth's magnetic field was very weak, because there are geological evidence that has happened. Okay, so again, this is a chapter focused on the Lorentz force. Okay, so that's a review of this chapter, the summary. Any questions?
I had a couple of questions,
Yes.
Professor. You were
Mhm.
talking about the high energy particles become trapped in the Earth's magnetic
Yes.
field.
Mhm.
But what is like the life cycle of that? Are they trapped forever, and do they just accumulate inside the magnetic field and bunch at the poles, or do they eventually escape back to space? Or
No, they don't. They don't live forever because they collide with the Earth's, with the molecules of the atmosphere, and they can impart energy. And when they have less energy, then they're not that harmful anymore. Yeah. So they don't live forever.
so okay, so as their energy reduces, then their radius would reduce, right? Because the velocity decreases as their kinetic energy decreases.
Well, when the velocity yeah.
Okay.
Yeah.
Okay.
But what
And then
makes
I
them
guess
harmful?
eventually they just kind of like reach an equilibrium with the rest of the atmosphere.
Yeah, I mean, compared with the air molecules, that's a very small part, very, very small percentage. Yeah, it's not like, you have like 10% of them are foreign particles. No. It's a very, very small amount. But what makes them harmful is their extremely high energy. But by colliding with the air molecules near the two poles, they give up most of the energy. So they're no longer harmful anymore. And then when they do reach the surface of the Earth, they're not harmful anymore. Yeah.
So is that how like ozone is made then? With like
ozone, well, it's part of the mechanism. Yeah, it's not the entire way the ozone are produced, but they can give energy to the oxygen molecules. Yeah.
I had a question on the way we were using the Lorentz force, because in the book it says it's equal to like the sum of the magnetic and electric forces. That is how I should be seeing it, right?
Well, it's a good question. Some textbooks say the Lorentz force is the total force of both the electric field and magnetic fields. It's QE plus QB cross B. And you're right, I've seen books like that. And in other books, when they use the Lorentz force, they specifically refer to only the magnetic part. So yeah, it depends on which book you use. But yeah, if you want to be more specific, you can say the magnetic force.
Okay. For this summary though, or you?
For this summary,
referencing
I have been focusing only on the magnetic part of the Lorentz force.
Okay, got it. Thank you.
Yeah. Very good. Any more questions?
Yeah, I was also going to ask in the motor, you want it to continuously spin, but the torque wants to just like flip like this and oscillate, right? I don't know. I was looking into it, and they said there was a device called, I think it was a commutator or something like that.
Yes, commutator.
A commutator.
Yes.
And I was curious exactly how
it's a clever device that reverses the polarity keeps the current flowing in the same sense, even though the power supplied is AC. It alternates. Yeah. It's hard for me to describe it, but if you see an animation of how this thing works, it makes total sense to you.
Okay.
Yes. Yeah. Otherwise, we can only use DC motors. But most motors are AC powered, and you have to use a commutator.
You could do it with DC too, right? If you just turn the current off, and you kind of just like give it a push, and then you turn off the current, and then you let it, and then you wait till it gets to the right spot, and then you turn the current on.
Yeah, but you certainly don't want to do that, right?
You certainly
don't want to do that because the motor turns, many
Right.
RPMs. It's impossible for you to,
okay.
right? Yeah.
Too difficult to time. Okay, for a good motor. Okay, I see.
Yeah. Okay.
I had
very good. Yes.
Sorry, one last question about. I was trying to think a lot about how like the magnetic field of planets relates to like the positive and negative charges, and like I had a friend ask me like what determines whether like a magnetic field or like even in a magnet, what would make it like north or south. And so I was just trying to think of what the electrical part of the magnetic field of the Earth is doing. Is that like for next chapter still? Because it's like,
well, in the next chapter, you will see precisely the direction of the current as it relates to the direction of the magnetic field it produces.
Okay, yeah, that's definitely.
Mhm.
Thank you.
You're welcome. All right. Any more questions, folks? All right. So here's what I'm going to do. I'm going to walk through with you a sample problem of this chapter. This one is a little bit. First of all, there's only one for this discussion, and secondly, it's a little bit different than before because I'm only going to go over half of that, and the other half I want you to complete it. And as an incentive, it will be an extra credit opportunity. Okay, so let me share that with you. Okay, hold on, it's coming. You see it, right?
Yeah.
Okay, this is from the textbook. Okay, figure TP 28.1 in the 10th edition. I'm sure in older editions they have that as well. So what you have here is a loop, is a current loop. What you're seeing is a side view of the current loop. Okay, side view. I mean, you have a current loop like this. Okay, so what you're seeing is this side. You're seeing from the side this way. You're seeing it this way. Okay, and it's pivoted right here. It's pivoted in the middle like this. It can turn about this axis in the middle, which is 0.0. Okay, and it's exposed to a magnetic field with a current running in it. Here is the current. Here comes out. Here the current comes in. So in the three-dimensional drawing, if I use a different color, I see the current coming this way and the current going out that way. Okay, the current is like this. Okay, and as a result, if you don't do anything else, it's going to turn. How does it turn? It's going to turn this way. It's going to turn this way. Can you see why it turns this way? Well, there are a couple of things we can do. If you already studied this textbook for this chapter, you know that there exists a magnetic torque acting on this current loop, and the magnetic torque equals to mu cross B, the magnetic torque magnet. Okay, and what's mu? Mu is defined as I times A being the vector area of this loop. You say, how does the area acquire a direction? Well, the vector, this vector A, the magnitude is just this area. And the direction is defined by using the right-hand rule, and that is, you see the current flowing like this, right? The current flowing like this. Okay, if you use the right hand, stick out your right hand and wrap these four fingers of the right hand around the direction of the current flow, and then this thumb tells the direction of the vector A. So in this case, the vector A points this way. It doesn't point back down, right? So because of the right-hand rule. Okay, you define mu as the so-called magnetic moment of this loop. Then it turns out there is a magnetic torque acting on this current loop, mu cross B. You can, I mean, I'm not going to go repeat the derivation here. It's in, we've gone over that, but you can see clearly it's making it turn like this. Okay, it's making it turn clockwise. The magnetic force is making it turn clockwise. Look at the Lorentz force acting on this segment. Hold on. On this segment, which is right here, right? The current sticks out of the screen, right? This red dot indicates the current sticks out of the screen. So if you use the right-hand rule, the magnetic force goes like I cross B. So I points out of the paper or the screen. B points to the right, so I cross B would point upward, right? And similarly, if you look at the force on that segment of the screen, it points downward. So overall, you get a torque turning it clockwise. That's the magnetic torque. Okay, now if you don't do anything else, this actually becomes a motor. It just keeps on turning. But we don't want it to keep on turning, so we attach a spring to it. Okay, the spring's attached to this end here. So the spring exerts a force pulling it back. So that is a backward torque, right? That's a backward torque. And at some point, they reach equilibrium. So which means the net torque equals 0. What they want to know is what this angle theta equals to when that happens. Okay, what is this angle equal to when they reach equilibrium, mechanical equilibrium? Very simple. Just make the two torques equal to each other. Okay. Again, here is the magnetic torque. So the magnetic torque, you know, the magnetic torque and the torque of the spring, they have opposite direction. We know that for sure. To balance it, just make sure they have the same magnitude. Okay, they have the same magnitude. So what is the magnitude of the magnetic torque again? It's mu cross B, the magnitude of mu cross B. So let's figure that out. Okay, mu has a magnitude. So the magnetic torque, as far as the magnitude is concerned, is mu B times sine of the angle between mu and B. Mu goes this way, and B goes this way. The angle between them is just theta. So you know the definition of cross product, right? It's first magnitude times second times sine of the angle between them. So it's mu B sine theta. Okay, and mu is I times A. A is the area, which in this case is B squared. Okay, here is this loop is a square of side length B, because B squared, and then times the magnetic field B, and then times sine theta. This is the magnetic torque, the magnitude of the magnetic torque. Okay, in the meantime, what is the magnitude of the torque provided by the spring force? Okay, now the spring force points this way, points downward this way. And you recall torque equals force times lever arm from physics 1A. Okay, the lever arm is a length starting from the pivot point and running perpendicularly to the line of action of the force. So this is lever arm. This red line is the lever arm. Okay, so what is the force? What is the torque? What is the mechanical torque equal to? The mechanical torque produced by the spring constant K is equal to force of the spring Fk times the lever arm, which is this guy, which we call L. Okay, and what is Fk equal to? It's just K times X. K times X. X is this extra length. Okay, and you have L. All right, we just have to express K is already constant. I just express X and L in terms of the angle theta, because I'm looking for the angle theta where equilibrium has been reached. The angle theta here, this is 90 degrees. So this angle plus theta equals 90, which means that angle is also theta. Okay, that angle is theta, right? And so from here to there, I have B over 2. This angle is theta. So how long is X then? X is equal to B over 2 times cosine theta, isn't it? Right? B over 2 times cosine theta. That's X. And then times L. L is this red line, which is B over 2 times what? Sine theta. So that is the torque produced by the restoring force of the spring. Okay, so upon equilibrium, I want torque produced by the magnetic field equal to the torque produced by the spring. Okay, and so just equate them, right? You have I B squared B sine theta equals K, and then in B over 2 squared sine theta cosine theta. Okay, I'm looking for the angle theta when it reaches equilibrium, and you know, you can easily solve that now, right? You cross out sine theta and you just left with cosine theta. Okay, so that tells me where the equilibrium takes place. In fact, why don't I call this angle theta naught? Theta naught. I'm going to use a subscript theta naught to indicate that this is equilibrium. Okay, now here, this particular place, I cannot call it theta naught because it's just general angle theta. But here, when they're in equilibrium, I'm call it theta naught, and theta naught. So you can solve for cosine theta naught equals whatever. Okay, so that is the equilibrium angle. Any questions? Okay, That is the problem from the textbook, which I want to share with you. So here comes the extra credit, folks. What do you think I will do? What do you think I will ask you to do for the extra credit? Which is the continuation of this problem. What do you think? Well, what if theta is not equal to theta naught? So if I push a little bit further, for example, beyond theta or a little bit less than theta, so it's not quite in equilibrium, right? And then let go, what's going to happen? The torque is not zero, right? The torque is not equal to zero, so it's going to start to turn. When it reaches the equilibrium position theta naught, do you think it's going to automatically stop? Well, it had some rotation, right? And at equilibrium, the torque becomes zero. When torque is zero, but you're still in rotation, do you stop immediately? You don't. You will overshoot. But when you overshoot, at some point, the torque is very strong, so you can turn. So what do you have? What happens next? You're going to have an oscillation, okay? You can have an oscillation around theta naught. Okay, so assuming that you do not have a large angle oscillation. Okay, so set theta equals theta naught plus a very small angle, which I call delta. Okay, the absolute value of delta is a lot less than theta naught. So we're talking about small angle oscillation around equilibrium. You're going to see a simple harmonic oscillation for a small angle. Anytime you have a small angle, small displacement away from equilibrium, what you let go, you're going to get a simple harmonic oscillation. Okay, my question is, what is the frequency? What is the frequency equal to? So you have to go back to physics 1B a little bit here. Even though the torque is, we're looking at magnetic torque, that's something new. But once you find the net torque, how do you find the resultant frequency of the oscillation? That's something that you need to work out for extra credit. Now, I'm not going to let you just start from nothing. I will give you some idea how to get things started. Okay, so I want you to find the net torque. Okay, the net torque. Now you can see from the direction of the torque, when theta, when you go from the 90 degrees, which is the first case, to that next case, when x goes from 0 to a finite value that you see, the magnetic torque is what makes this thing go further. Okay, the friction, the spring torque is what makes it go back. Okay, so you can find a net torque. You can find a net torque. If I call this direction positive, then you can find a net torque, and which is equal to what? F torque net. That's magnetic torque minus the torque of the spring, right? And what is that net torque equal to? Torque equals I alpha. Remember that from physics 1A? I alpha. Okay, and this I here, that's not the current. Okay, make sure you understand that we call it I about 0.0. Don't worry about what that IO is. Okay, IO is given. You can just put it on this. Don't worry about it. Okay, but how do you express alpha? Alpha is how fast this angle theta changes. Actually, how the angular acceleration changes. So alpha is related to the angle theta. So you start from there. Okay, but make sure you utilize this condition, small angle approximation. Okay, so eventually you are going to get, hopefully you're going to get something times theta, something times delta equals to the second derivative of delta. Hopefully, okay, if you did everything right, you're going to get something like this. And this will lead to a simple harmonic solution. The details, if you forgot, you can go back to chapter 15 of physics 1b and take a look how we do that. Okay, but I have given you the expression for torque, for both torques and an arbitrary angle. You just have to expand, you have to approximate it when the angle theta is, not too far from equilibrium position. And then you can simplify the math and see what happens. Okay, this is extra credit. I mean, the calculation is a little bit more involved. It's not something I will let you do for a test or even for a regular exercise problem. But I'm going to establish this extra credit, and you can turn it in. I'll give you, a couple of weeks to do that if you're interested in doing the extra credit. Okay. Did I make it clear what I want you to do?
Delta is an angle, right?
Yes. Yes.
Okay.
It's a tiny angle away from the equilibrium position.
Okay.
Yeah. So that's the variable that you want to establish an equation for that variable. So that's your target. Okay. The target is that last equation. Yeah. Okay. Any more questions, folks? All right. So that's it for the discussion of this chapter. What I want to do now is I want to walk you through today's lab, which is RC circuit. Okay, so let's go back to I'm going to go back to desktop now. Okay, so I'm going to use desktop. RC circuit. You know the theory for RC circuit. All right. In our PCC lab room, we have a simple setup of one resistor and one capacitor in series. Okay, and powered by well, depends on whether it's charging or discharging. Charging, we have a battery. Discharging, we have nothing. We have just a cable. But the charging and discharging process, the time constant is R times C. And the thing about C is that you don't get 1 farad capacitors. These are just gigantic capacitors. You don't even think about getting 1 farad capacitor. A farad is a huge number. It's a huge magnitude. I mean, when you go back to chapter 26, we talked about that. Okay, like 1 volt is nothing. 1 amp is nothing. 1 ohm is nothing. Okay, but 1 farad, that's a huge, gigantic capacitor. Even a millifarad is considered a very large capacitor. We're typically getting microfarad, nanofarad, or even picofarad. Okay, pico is 10 to the -12, as you know. So R times C, even though let's say we use like 1,000 ohms, a kilo ohm, right? That's a pretty big resistor. R times C, it's still usually very small, a lot less than 1 second. Okay, because C, we're talking about 10 to the -6, or even 10 to the -9, 10 to the -12. So R times C, typically in a typical circuit, we're looking at R times C about like a millisecond or a microsecond. Okay, so when you flip the switch, you turn it on. How long does it take for them to charge up? It typically, like after 3 time constants, is considered pretty much fully charged. But each time constant, we're talking about under 1 millisecond. Okay, so there is no way for us to measure, within a millisecond what happens. I mean, we humans don't have that kind of reaction. So we have a device to help us do that. That's called an oscilloscope. Okay, and an oscilloscope is gives you a visual presentation of voltage as a function of time. And a time scale, we're talking about milliseconds. Okay, talk about typically milliseconds. And then for discharging, all we have to do is just to replace that battery with a flat, with a wire. And you can switch from charging to discharging automatically by using using a voltage signal which alternates between epsilon and 0. So when it's epsilon, it's charging. When it's 0, it's like a Y, it's discharging. Okay, that's what we did we would do it in a real PCC lab. And since we're not doing that, we're doing only it's not a simulation. It's actually, we're getting data from an actual lab done by somebody else. So this is what we're gonna do. you're gonna first take a look at how they did it. Okay, so this is the video. Okay, you can play that video. It's only about 11 minutes long. So they have a circuit like this.
Understanding.
And okay, it may look a little bit confusing. Where is the resistor? Where's the capacitor? Well, trust me, it's all there. And they explain to you where the resistor is, what the capacitor is, and so on. And they also, if you watch further, they use a device which is similar to our oscilloscope to display the voltage for the charging and discharging. It's a very quick process, so you have to capture certain moments. See how fast it is? Okay, charging and then discharging. You have to isolate that part and isolate that part. But in my write-up, I describe you how to capture those moments. Okay, so let's go back to here. And their circuit is a little bit more complicated than the single RC circuit. So here is their circuit. I made a write-up to show you how that is done. Okay, so that's, but I have a bigger picture I can show you. Okay, let me show you. So this is their circuit. It's actually, it's got two resistors, R1 and R2. R2 is in parallel with the capacitor. Okay, what you're measuring is the voltage across the capacitor, VC. Okay, the thing is VC equals to the voltage across R2, right? Do you understand why? Because R2 and C, they're in parallel. Can you see that? They're in parallel, right? So they have the same voltage. What is the voltage across R2? It's just I2 times R2. Isn't that true? That's Ohm's law. So if you can solve for I2 times R2, that is the voltage across R2, which is also the voltage across the capacitor because they're in parallel. Okay, so how do you solve for I2? And don't forget, there's also an I1. This current I splits into I1 and I2 by Kirchhoff's rule. Okay, so you need to establish two equations because there are two unknown currents, I1 and I2. So it's a double loop circuit, not a single loop circuit. So that's why it's more complicated than our case. But to make your job easier, I did some analysis for you here. I equals R1 plus I2. That's no rule. And the loop rule, here is a loop rule. I1 equals D. Okay, I1 equals dq dt. That's how we relate I1 and Q, which is this. And you realize also VC equals, this VC here equals I2 times R2, which is, I replace VC with I2 times R2. Okay, so that gives a second equation relating I1 and I2. Turns out I1 equals CR2 times di2 dt. I1 and I2 are not proportional to each other, but I1 is proportional to the derivative of I2. You can see here. Okay. Now, if you, and then of course that is the loop rule. Epsilon equals this voltage plus that voltage. That's epsilon. Okay. So, given these three equations, which I hope you understand by now, you can solve for. You can get rid of I and I1. I don't want I don't want I1. I only want I2. Why do I care about only I2? Because again, I2 times R2 is the voltage that you read here across the capacitor. Okay, so I'm looking for I2. Here's the equation for I2. You see here, dot, 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 and dot, dot, dot. I want you to find what this is and what that is. So you say, how do I find it? From these three equations. Just simplify these three equations. Eliminate I and eliminate I1. You will get this. Okay, you will get this. So in your lab report, you need to tell me what this is and what that is. I already did most of the work for you. Okay, just to do the algebra. Okay, so here is the equation for I2. And then this is a typical equation, differential equation that we can use to solve for I2. And I2 starts from 0 and it goes up like this. Okay, it goes up like this. And then from that you can fix these constants I maximum and alpha. Here's a solution. Here's the generic solution for this equation. So what is I maximum? What is alpha? Alpha is determined by those numbers here. Okay, once you find what these are, I maximum is determined by what happens at the very end when t goes to infinity. When t goes to infinity, this term becomes 0, e to the negative RT becomes 0, so I2 becomes I maximum. But at t equal to infinity, this capacitor is fully charged, right? When it's fully charged, what is I1? I1 is 0. There's no more current flowing through it. So I goes only to I2, the I becomes equal to I2. So you just have a single loop like this for the current to flow. And the current flows through both R1 and R2, powered by epsilon. So epsilon will be equal to I times R plus R2. That's the final stage. So that is the value of I2 when t goes to infinity. Okay, because there's no more current running through, charging up the capacitor anymore. So you can find what I maximum is, which is right equal to this. Okay, so that will give you the theoretical curve for VC, the theoretical curve of VC. Okay, which is what you see here, And again, the only part that's interesting is this little part. So you have to blow up that part, and you can get a more detailed reading. Okay, and by detailed reading, I mean you read, you collect some data points. Okay, like this point, this point, this point, this point, this point. Collect a number of data points for voltage and time. Time has to start from here, not from there. Has to start. You have to set 0 here. Okay, and then what do you do once you have these data? You can turn this linear equation into, turn this exponential expression into a linear equation. The way you do that is by solving for, move everything to that side, leaving only e to the power negative alpha t, only e to the power negative alpha t. Just rewrite it and take natural log of both sides. Immediately, you eliminate that t exponential anymore. There's no exponential anymore, okay? Because natural log of e something equals something, right? Natural log of e to the power x is equals just x, right? So you don't have the exponential anymore. And you plot the entire natural log as the vertical variable, and the horizontal, you just call it t. So you get a straight line, the slope is negative alpha in theory. You know what the theoretical alpha is. It depends on R1 and R2 and C, okay? You compare with what you actually plotted, because when you do the plot from the data, you're going to get your slope. How does that slope compare with the theoretical value, alpha? I didn't tell you what alpha is. You're going to find out yourself. Again, it depends on R1, R2, and C. You work that out yourself from these numbers, okay? So that's charging. Now, discharging. How did they do discharging? When they do discharging, they no longer have that battery anymore. They don't have that battery anymore. Okay, this thing is fully charged, and they remove the battery, and they open that switch. When they open that switch, there's no current flowing through R1 anymore. You have only one loop like this, only one loop like this. So that is very simple. It's a single resistor, R2. There's no R1 anymore. R1 has been taken out because you open that switch. R2 and C. The discharging curve, we studied that in the lecture. It's the same exact thing. Okay, so I didn't bother to let you work anything out. This already worked out for you, which is something you should easily understand. If not, you can repeat these derivations yourself. Okay, and then you have this. All right. So that's the slope. And here, I tell you what the slope is, because that's a standard result you already should have already known from your study of chapter 28. Okay, so that's the theory. It takes a little bit of effort to sort things out here, but we're not collecting data ourselves. Somebody collect data for you, so that's why we put some more effort here in return. Okay. So the details, as far as what we need to do, they're all here. Any questions, folks? Okay, so that is the RC Circuit Lab. And that is what I plan to discuss today. So one last time, any questions?
Sorry, Professor, yes. Do you want us to work out the equations in the lab reports, like from the beginning, the system of 3?
Yes, yes.
Okay.
That's something you should do. We also have a PCC lab manual, so that's something you should read first. Okay, except the PC lab manual has only R and C in series. So the discharging part is really the same theory. The charging part is something here is more complicated, so you have to work it out. But I already gave you the equations. So if you really want to exercise your, what you want to do is don't look at my equations. You just look at the diagrams. Okay, just look at the diagrams. Just look at this diagram and come up with your own equation. Do not look at those. See if you can come up with the equation that I wrote. That would be even better. Okay, but at the very least, what you should do is read my equation, make sure you understand each line. Okay. All right, any more questions, folks? Okay, in that case, I'm going to stop the recording now.